Fine. So, announcement. We have 2 class observations. They're observing me, not the class, so not you or anything you do, but 2 observations on next Thursday and the following Tuesday. So you don't have to do anything differently. I just want to let you know that someone will be in the class observing me. Okay, so questions on the homework? All right. So 3.8, we're going to look at implicit differentiation. And you may or may not be aware that when we define functions, typically we see them defined explicitly as y equals to a function of x. You can define functions implicitly, where it's implied that y is a function of x, where you may or may not be able to see what the function actually is. Like, you know, we'll look at the example in a minute, like the circle centered at the origin with, you know, let's just say a radius of 1. Like that's an implicitly defined function, because we can solve for y in terms of x. So we really haven't seen much of that up until this point, which we're going to look at extensively as far as the derivatives are concerned. So implicit functions, for like the unit circle, we can explicitly solve for y. So even though like it's x squared plus y squared equals 1, it's implied what y is in terms of x. We can actually solve that and say, okay, well, here are my 2 functions of x, plus minus root 1 minus x squared. Some functions, like example 2 here, the sine of x cubed, y squared, etc., some functions like that cannot be solved for y. You cannot explicitly say y is equal to this stuff in terms of x. So with that in mind, since some functions we can't explicitly solve for y, we need a different method to take derivatives of those types of functions, which is what 3.8 is about. So how do we take the derivative of a function that's defined implicitly as opposed to explicitly? So the operating assumption is that y is a function of x. We just may not be able to determine what that function of x is. Okay? So even in this section here, y is still a function of x, even if we can or cannot get a representation for it. So this section relies heavily on the chain rule. And before we actually start talking about this, let's just ask a question. What is the derivative of how do I want to do this? We'll just say this. What is the derivative of f of x to the 3rd power? With respect to x. So just with respect to x.
Take a stab at it.
Okay.
It's probably going to be wrong. Is it 3 times f of x squared times f prime of x?
Yeah, that's exactly right.
Okay.
So we don't know what that function of x is, but you know, like what if I said take the derivative of sine x cubed. So let's just look at the derivative of sine x cubed. We have to use the chain rule, and we take the derivative of the outside, leaving the inside alone, right? And then multiply it by the derivative of the inside times the derivative of sine x. So that's the same process we do here. The derivative of this is 3 times f of x squared. So there's the derivative of the outside, leaving the inside alone. Then we multiply it by the derivative of f. So put anything in there, e to the x, natural log, whatever that function is, that's how we take the derivative of it. Is everyone all right with that? Are there any questions on that? That's the fundamental rule or property that we're using to take the derivative of functions implicitly. So since y is f of x, we could say that the derivative with respect to x, of y to the third power, it's the same thing as taking the derivative of f of x to the third power, because y is f of x. So the derivative of y cubed with respect to x is a very similar flavor here. What would it be?
3y squared times derivative of y.
Right. So it's just 3 times y squared times the derivative of y. Again, think about y as a function of x. In this particular instance, sine x is y. We were happy, whatever that was starting out, we were able to solve for y and say that y is equal to sine of x. But I could have just as easily said it's 3y squared times the derivative of y, right? Knowing that y is sine x. But again, most of the functions we deal with, we don't know what y is. It's just kind of hanging out as y.
And the second one, y3, wouldn't it be the derivative with respect to y, or minus?
No, we're still taking the derivative with respect to x because y is a function of x. Yeah. So if we said, it totally changes the game if we say take the derivative with respect to y of y cubed. What's the derivative with respect to y of y cubed? It's just 3y squared, right? Just the same way we take the derivative with respect to x of x cubed, and we say that's 3x squared. So it's a subtle difference, but it makes it has a huge impact on like how we work these and how we think of these. Any other questions or comments? All right. So what we're going to look at then is we're going to look at the derivative or the slope of the tangent line at points on the unit circle, and we're going to look at it explicitly because, you know, like I said, in some instances you can solve for y. So in this particular instance, we're going to look at this derivative explicitly, and then we're going to look at it implicitly. And just verify that the results do line up. It is the same result. And so we're just going to kind of use this example as, our acceptance of the fact that implicit differentiation works. So when we get to functions where we can't solve for y, we know that it's still going to work. So explicitly, to take the derivative of this, we have to solve for y first. And so y is, as we wrote on the first page, the plus or minus square root of 1 minus x squared. So notice we have two different functions. And why do we have two different functions here?
Because of the square root.
Because we're solving for a square, right? Why else do we have, or in terms of the circle, what does it mean to have two different functions describing the circle?
You have the top half of it and the bottom half of it.
Right, you have the top half of the circle. Negative. So this here gives us, this is the equation for the top half of the circle, because y is positive, right? Y is the positive root, so that's all values where y is positive. Oh, it's goofing up again. And then the second negative root describes the bottom half of the circle. So any points on the bottom half of the circle are described by that equation, and if we want to find the slope of the tangent line at any point on the unit circle, we have to ask, first of all, where is that point? Because we're going to have two different derivatives, because we have two different equations. So like the point here, 1/2 comma root 3 over 2. If I wanted to find the slope of the tangent line at that point, then I need to take the derivative, or look at the derivative of the positive root 1 minus x squared. All right, so that's kind of what's happening there. And let's look, so we'll look at the derivatives individually. What's the derivative? What's the derivative of root 1 minus x squared?
2x.
Yeah, that's part of it. You're right. So chain rule. You've got 1 minus x squared to the 1/2. So we chain rule. Take the derivative. Power comes down. Inner functions left alone. And then we multiply by the derivative of the inner function. So we've got a negative 2 times 1/2 gives us a negative x. Over the divided by the square root of 1 minus x squared. And again, this is our derivative for the top half. So, or slope of the tangent line. At points on the top half of the circle. The bottom half of the circle is just the negative of that. So y is negative root 1 minus x squared. So if the only difference is the negative in front of the function, what do you think the derivative will be?
X over root 1 minus x.
Yeah. It's the opposite of our derivative, so it's just x over square root of 1 minus x squared. Oops. And so this is the slope of the tangent line, or derivative, the bottom half. Does anyone have any questions on that? So do these two results actually make sense in terms of our unit circle? So notice the derivative for the top half of the circle is negative, right? We have negative inputs for x, or sorry, negative inputs on the top half of the circle. If we plug in, for instance, at this point 1/2 comma root 3 over 2, the x value is 1/2, but if we look at the slope of the tangent line, is the slope of the tangent line at that point positive or negative?
Negative.
Yeah. So we see that the slope of the tangent line there is negative. We plugged in a positive x, and we get a negative as a result because of that negative right there. If we looked at its mirror image over here, somewhere over here we have negative 1/2 comma root 3 over 2. What's the slope of the tangent line at that point? That slope is positive. So we have a positive, oops, that's not a line, close enough. But this is a negative slope. We plugged in a negative x, and we have a negative of that negative x, which gives us a positive. Same thing with the derivative for the bottom half of the circle. It's positive x over the square root. So we can reason the same way. If I plug in a point here, like 1/2 negative root 3 over 2, the slope of that tangent line is positive. But I'm plugging a positive x into this equation right here. So it's positive x over something that's positive, which gives us a positive slope. So in that way, we can sort of say, yeah, it seems to be fitting with what we're looking at visually. Yeah.
Isn't the slope in quadrant 2 positive as well?
Yeah.
You wrote negative.
Oh, I wrote negative. Okay, sorry.
You were thinking about the negative half, I think.
Yeah.
I'll cover for you.
Yeah. Thank you. Yeah. Thanks. So, we could reason through it that way and see that, okay, well, I can solve for that function explicitly. In other words, I can say y equals to this stuff involving x and take the derivative as we normally have, and everything is fine. So let's look at how we take the derivative of that equation implicitly. We've already alluded to how we're going to take the derivative with the piece involving y. Another way to think about this is that we have x squared plus y, which is some unknown function of x. From what we just did, we already know what that function of x is. It's positive negative root 1 minus x squared. But we're going to pretend that we don't know what that is, because this is our general approach to these types of problems. So y is f of x, we'll just replace it that way. So then we just take the derivative of the equation as it is. With respect to x. Okay. So either one, whatever makes sense for you to write down or how to think about that, it doesn't matter how we express that. So then we take the derivative of the left-hand side. We're going to take the derivative of x squared plus y squared with respect to x. The derivative of x squared will give us what? 2x plus the derivative of y squared. 2y.
2y times y prime.
So again, 2y is accurate if we're taking the derivative with respect to y. We're taking the derivative with respect to x. Again, if we're taking the derivative of y here, we have to say it's 2 times f of x to the first times the derivative of f of x. So it should be 2y times y prime. And so that's what you'll see is as you take the derivative implicitly, you think about just taking the derivative with things that involve y as you normally would, but then you always have to multiply it by y prime. That's really the only addition we have here. It's sort of oversimplified when we say it that way, but in practice, that's just how it comes out. Take the derivative as you normally would, and then multiply by y prime anytime a y is involved. And the derivative of the right-hand side, the derivative of a constant, is 0. So notice since that function was implicitly defined, we have a implicitly defined derivative. But all we need to do at this point is solve for y prime. Because we want to know what the derivative is. We want to know what y prime is. So, whatever, subtract 2x, divide by 2, 2y, divide by 2 first. However you want to get there. So y prime equals to negative x, which means y prime is negative x over y. And here we would say that, of course, y cannot be 0. We'll look at that in a second. So there's the derivative of our unit circle. And notice what we end up with, where in this setting, what we didn't end up with in the implicit setting was we have a derivative that's in terms of both x and y. So if we didn't know what y was, like most of these, like I said, you can't solve for y. So we're not going to know what y is in terms of x. But again, just to reinforce the idea, does that derivative negative x over y actually make sense from our prior results? What we had before this, we knew that y was equal to this thing here. So does our derivative implicitly make sense? We have y prime is negative x over y, which we kind of need to split up, right? Because we have two representations for y. We have negative x over y and negative x over y. So does that match what we had when we took the derivative implicitly? Yeah, we have the negative x over the root, and then we have this negative and negative making that positive. So we can use this example like we just did to verify that the two methods do give us the same result. This one's right and this one's right. So the only difference is if we've got this derivative we took implicitly, negative x over y, and we want to go back to one of those points or any point on the unit circle and say, well, what's the slope at 1/2 comma root 3 over 2? Instead of this setting where we just had to plug x into our derivative to get that slope, in this setting we have to plug a negative or x and y into that expression to get the slope. So that's the only difference. Oops. I don't know what happened there. We'll do negative 1/2 root 3 over 2. So looking at 2 points on the unit circle, using our derivative negative x over y, we can come up with the slopes at each of those points. So instead of, like in the explicit setting, we ended up with 2 different derivatives for y depending on what part of the circle we're on. Implicitly, we just ended up with one derivative, and it sort of takes care of itself what part of the circle we're on when we plug in that ordered pair xy. It's already there. So at the point, what do we have? 1/2 root 3 over 2. We have negative 1/2 over root 3 over 2, which gives us negative 1 over root 3. And of course, since the point 1/2 root 3 over 2 is in the first quadrant, like we said, we had a negative slope at that point, which is validated here as a negative 1 over root 3. This point, example 2, that's in the second quadrant, where we said that the slope on the circle should be positive, and indeed we come up with positive 1 over root 3 for that slope. So questions on that example? So like I said, we use that example just to verify that the method of implicit differentiation actually matches with our other derivative methods that we've had up to this point.
Does it matter about leaving the
Huh?
root? Does it matter about leaving the root under the denominator?
I don't think so. There's so much emphasis on rationalizing denominator. I don't really know why. I don't care.
That works.
I don't think it matters. I don't know why that became a commonplace thing in math to say that it's improper to have a root in the denominator. I don't know who came up with that, but it certainly stuck.
Yeah.
I don't care. Because, I mean, I don't know the number 1 over root 3 any more than I know the number root 3 over 3.
Right.
Like, I still have to plug that in my calculator, right? So, yeah. All right. So, still keeping with this example, when we said that the slope of the tangent line at any point on the unit circle is given by negative x over y, and we said from the derivative, it's clear that the derivative function y can't be 0 in that derivative function. But what happens in that sense? If y is 0, where are you at on the unit circle?
On the x-axis.
On the x-axis, right? It's an x-intercept. So the x-intercept of the unit circle is here and here. What's the slope of the tangent line at those 2 points then based off of this?
Infinity.
It's not defined, right? Because if the denominator, if the y value is 0, which it is at those 2 points, then you have an undefined slope. More particularly, the slope is becoming more and more vertical. So we have, in that sense, we have vertical tangents. in our derivative negative x over y. What happens when x is equal to 0?
Horizontal tangent line.
Right, good. When x is equal to 0, and we should say y not 0, when x is 0 but y is not, the derivative is 0 itself, right? So we have the slope of the tangent line is 0, which means we have a horizontal tangent line, right? The derivative is 0, horizontal tangent line. So we see when x is 0, we're at this point and this point, and we're just visually validating that we do have a horizontal tangent line here and a horizontal tangent line here. All right, whatever. That's tangent at that point. It's not cooperating. Okay, so all of that stuff still coincides with these derivatives, even if they are expressed in both in terms of both x and y. It still all fits. Anybody have any questions? Okay then, so we'll find the derivative of this curve, x squared plus xy minus y cubed equals 7. So I want to take a few minutes to get that derivative.
Yeah, that's fine. So the only place where you and I diverge is how we go with this right here.
Yeah.
How we go with that x times y.
So I did this down here, and I did the product of it. And so I did first times the derivative of the second. That
So,
plus
okay, so
the second times the derivative.
So did you do x times y prime and then 1 equals y? because we can't define the y.
Well, that's why you can go to x to y prime.
Okay.
Because I
How did you get the
So I probably did it wrong, but I did it the same way I would have found this derivative of x. Because you assume that x is the one exponent, and then you take that to the front and then subtract one, and then you back on the y prime.
But it would be x to 0, so it would be 1.
Anything raised to the power of 0 is 1.
So.
Because you're
this-
subtracting like 1.5
Okay.
on the power.
So then this would actually be.
That'd be that.
Yeah, that would be 1, yeah.
And then this
And-
would also be.
Yeah, and then absolutely everything clears up, because then it matches.
Okay, so then that would be one, so that would be one, which means that, right?
It's just like
Sorry. So, but you would still have to leave on this one, y prime, right?
Yeah.
Because.
Yeah, we would.
Yeah, but then
Can you
this
explain
y
that?
would just be fine.
Yeah, yeah, because it's just, it's hanging out there,
Yeah, I have
and
that.
there's no
You
like
wind up
terms, so,
with-
yeah.
Okay, so now I should probably try to take the next step. We're just gonna see how
The
that
first times the derivative of the second
Yeah.
plus the derivative of the
Solve for
first,
y prime, right?
which is just x to the power of 1.
Yeah, I
Bring that one up
suppose.
front.
Look.
Subtract that.
I'm doing my
Power of
best.
0 is 1. Just get rid of that x times the second. So that whole one.
See, this seems like a relatively simple function, and I already feel like this
So
is.
this whole product will go right here in terms of x and y prime.
I don't
Okay,
disagree
second question,
at
where
all.
did
What you really have there is you really have this,
Oh, that.
It's fine, but this makes it down.
Okay, so that.
yes, because y is f of x, y is some unknown function.
Like if I had somebody sitting there saying, this is what we want to get, this is what you're in.
So like, let's just say, what if you had this, how would you take the derivative of that?
2x
Well, I was thinking, you guys are available Sunday morning at any point.
Yeah, no, just for this one. What rule would you use to take the derivative there?
Like a quick hour, 2 hours.
Right,
like I said.
so replace sine with whatever function this is. We don't know what it is, right? You've got x times another function of x. You've got to use the product rule on that one.
I don't even know.
Is that it? Like, further?
Yes. Well, you have to, we're trying to solve for y prime. That's
Well, then you just get both y primes on one side of the y prime.
But can you even?
First thing we need.
So in essence, you have to take, you get 1 for x, you get 1 for y times y prime, and then 3y squared times y prime is 1. And then
Now, we only want the work
gonna
that
add
is
y
y
to go over as well.
Yes.
Take out that y.
Yeah, this where I was stuck.
Can you do
Yeah, on one of the
the left side divided by x minus 3y squared?
X minus 3y squared, yes. Yes, I believe it. So what, yes, there is, because what you do is you take the factor of y prime. So you have y prime
Yep,
times.
Look at you being really quiet. See, we were on the right track. It's true, two lights.
I still don't understand this part.
I like to imagine that that's what Isaac said every time he played.
So there's nothing more from this one to do. This is, I'm gonna assume.
Let's assume.
Good sense.
I wiped it out.
Paying attention. Well, maybe you're right for a moment. I was paying attention. Now I'm lost.
Oh, now we're just solving the lines.
That's what I was just looking at.
I don't know why you find it so funny.
Then you just
I don't know.
earlier you do x, and you did the same thing with y. You went with x y prime minus 3y squared y prime equal to 2x minus y minus y.
Or no,
And
one.
then on this side, since both of them y prime dividing out the other y minus on both sides.
So basically, we can.
Yeah.
Guessing.
Yeah.
So we can make one good math.
Yeah, and then you put in
Not there.
no, but
That's what it gave the derivative. Is it drawn?
Saw my sister.
That's why I didn't look at it. I was like, oh.
It's all fake.
Yeah, you should take a picture of it.
Like this. It was all fake. Like yeah.
I just need some more time.
I was like, see if I can get my sister showed me this.
There's no glue
This
going
app,
on.
you just take a picture of the problem and it explains how to solve it.
Sophia has not responded. And hers is still alive.
Probably. I had all of my derivatives in the
Oh, they got
Hold on. So I know that this was your favorite, but also I feel like I changed it.
Oh,
Yeah, you just take a picture and you solve
Don was like, we can do this, you just didn't have the right
I did that.
rules.
This was not going to be
Wait, what are we doing?
I don't know if
This was your good, but I still feel like I changed it.
By our powers of combustion,
I know my baby sister.
I know what to do. I should
Use
use
that. I'm
that.
like,
Can I get a comment? And maybe through osmosis, I can get some calculus patterns.
That's how I do it. I just surround myself with brilliant people and I'm like, yeah, this will work. And then I'm superstition.
because
I did elementary calculus today.
Yeah, the tiny computer said we were right, so. All right.
App
So to check this, online calculator.
We sorted it out. There was a lot of questions at first.
I just need to figure out what the factor is.
I honestly impressed that I got 10.
Wait, I got you too. I got you already. Yeah, I got you here. I got
Oh, the strength there.
These two are sticking. Like they're like. Right? Like this was a $4 check.
I want to see the research behind that one.
But I'm an instant gratification person. I guess
Everyone.
I found a very similar to that, but it was like which I still might go for at least past the second one.
You'll get to a point
Just because there's fun parts, and I suck at shit about prices.
This problem can't be solved, but I'm angry.
That's true.
Exactly. That's fair. I am constantly on the search for any favorites.
Tequila's an upper, everything else is down. So.
Like, head that I think is good, and then I find the next one, and then I find the next one. I don't like them. Like scratches. I like heads that don't feel like I'm writing. Which is how.
That's why I really
So like, pine salt, like, you're gonna drink the cleaning solution. Yeah, that was nice.
And so that's why I was so mad about scratching. But I think that we use
See, that's what I heard too. Like that night, like if you can soup enough, you got like 4.
So that XY term is a product rule. It's really x times some unknown function of x. So we have the first times the derivative of second, so x times the derivative of y, which is y prime, plus the second times the derivative of the first, y times the derivative of x is 1. So xy prime plus y is the derivative of xy.
How did you get that?
So it's the product rule here on this x times another function of x, which is a y. So you've got the first times the derivative of the second, plus the second times the derivative of the first. Right? So first times the derivative of the second. Huh?
Why are you only inserting one for one part of it?
Because that's plus the second times the derivative of the first. So that 1 is the derivative of x.
Wouldn't they both technically be one?
Yeah, why isn't it?
Yeah, I guess I don't really understand why you're putting one just in that spot, because if you really want to get technical, the derivative of any of those, since they're to a power of 1, is going to be 1.
The derivative of anything other than y, right? Because the derivative of y is y prime. The derivative of x is 1. I mean, you could multiply 1 here. You could say, well, was x times the derivative of y, which is y prime times 1. I don't know why you do that. Yeah, because like we said, the derivative of some unknown function of x, the best we can say is it's f prime of x, right? Once we know what the function is, we have specific rules to take the derivative of it. Like if I know the function sine, I know the derivative is cosine. But if I don't know the function, the best I can do is say the derivative of f is f prime, the derivative of y is y prime. That's the best I could do because I don't know what that function is. The only way I know what this function is, the only way I know what y is if I solve this original equation for y. Then I know what y is. But notice that's like, you're going to end up with 3 equations for y because it's y cubed. If you solve for a cubed, this red curve here is actually made up of 3 different functions coming from the y cubed. So we don't know what that y is. It's just like an unknown f of x. So when we take the derivative of it, we just have to take the derivative of it symbolically because there's nothing explicit there to take the derivative of. So we should just use that.
Alright, so I mean, if there's nothing explicit, we don't have any real values, I guess I still don't see how you're, well, I can see how, 1 would be what would go in the parentheses. I guess I don't really see the reasoning as to why you're putting it there and only there.
Oh,
And why you're only defining that.
we don't have to put that there then, if that's confusing. It's just the first derivative of the second plus the second y times the derivative of x, which is 1. If, as an intermediate step, you would have here the derivative of x, I guess, which is 1 times y, right?
Are you confused, like, why would it equal 1? Because I was confused on this.
So let's write it like this. What if you had sine x?
Yeah, I don't really.
What if you had x times sine x? You would say it's the first times the derivative of the second.
Right. Times the second, times the third, or plus second times the first.
Right.
So when you add it to the second, x is still there.
So you would have that, right? Well, we don't know, like we just have a specific function right here. If we have a generic function, it's still the same thing, except for we're just going to replace this with that generic function. Right? And that's the only difference there. Well, what's the derivative of f? I don't know. I can just label it as the derivative of f. If I knew what f was, I could tell you what the derivative was, but I don't. So that's your x times f prime, x y prime, right? And then here's your function y times the derivative of x times 1. So that's the only reason I put that 1 there like that, because that's the derivative of x with respect to x.
Why isn't f of x just 1?
F, well, why, what do you mean? Why is it f of
times
x
y
1?
prime, but it isn't right to 1. Or 1
Because
times y
it's
prime.
respect to x, not respect to y. Okay. If it was respect to y, then the f of x would be 1 and the x would be 2. Okay, right?
Yeah, I mean, you understood the question better than I did, so. Yeah,
Will it say that the question is with respect to x?
Yeah, say use implicit differentiation. And again, in this section where the underlying assumption is y is always a function of x. Otherwise, you're dealing with partial derivatives, which is a Calc 3 topic. So we're talking about y is always a function of x. Yeah, I mean, are there any other like questions or comments, or are people still confused? I mean, it's definitely odd to do this, especially when you've never seen it before. You kind of have to shift on how you think of things, which requires some effort.
So the real world application of this is once you find the derivative of y, like you've separated it out from everything, you can take any x, y coordinate and it'll tell you the slope.
Right, exactly. Instantaneous rate of change, yeah.
So what's the final derivative of this? Is it just x, y prime plus y?
Yeah, the derivative of the middle term, xy, is xy prime plus y.
Okay.
The derivative of x squared with respect to x is 2x. The derivative of the negative, or the derivative of y cubed, we'll do it here, is 3y squared times y prime. So everything is still the same, like I said. The simplistic way to think about this is if you take the derivative of y, take the derivative of it like you would if that were x cubed, right? So we would just say it's 3x squared. But when a y shows up, take the derivative and multiply it by a y prime. If the fact that y is a function of x is confusing or hard to grasp, I guess, then just multiply derivatives of y times y prime.
Or write it as f of x.
Yeah, right, that's kind of what I hoped would be a little bit more clear, but I think there's still confusion around that, so,
So,
yeah.
so if we have two y primes in that equation, that means we have two different y prime equations? Or?
No, so we do have two different y primes here, but the overall derivative is just y prime. So
But we're solving for y prime, right?
exactly, yeah, you've got to solve for y prime. Just because we have two y primes in the equation doesn't mean we'll have two different derivatives like we did with the unit circle when we solved that explicitly. So any questions on our derivative here? Then we've solved for y prime, so just like from algebra, the thing you solve for, you just want to isolate it on one side, right? Like when you solve for x, you get all of the x's on one side, and then you solve for x that way. You solve for y prime, everything with a y prime on one side. So we're going to leave the x y prime term, and we're going to leave the minus 3y squared y prime term on whatever side. Doesn't matter. We just want those terms involving the variable we're solving for, y prime, to be together. Everything else we need to put on the other side. So we need to put the 2x over here, subtract it, and the y over here. All right, since now both of these terms on the left have a y prime in common, then we'll just factor that out. Okay, so that's still negative 2x minus y, and then divide through by x minus 3y. So that is the slope of the tangent line on that red curve at any point. Any questions on this? Sure. Get it? All right, so let's look at one. Stick with this example and proceed a little bit further. Now, find the slope of the tangent line at the point 3, 2.
Okay, I'm sorry. Excuse me.
So this is our xy. So we just need to plug in our derivative, because that's the slope of the tangent line. We need to plug in x equals 3 and y equals 2. We just need to compute that value.
It's not my calculator, it's track.
So we get 8/9. So that means on this curve at the point 3, 2, that's at. At that point, the steepness of that curve is 8/9. So there's really two types of problems you can see here. One of them is just find the derivative, then you're done. Go on to the next one, find its derivative. The other problems involve either finding the slope at a point or the actual equation of the tangent line. So if you're asked to find the slope of the tangent line at a particular point, instead of solving for y prime, which can be tricky sometimes, from this step, once we've taken the derivative, we can say, well, the derivative m tangent at the point 3, 2, I can just directly plug in x equals 3 and y equals 2 in this derivative here. And then that way I'll just have a y prime to solve for, as opposed to like looking at all of that and trying to configure what y prime is. So if from the first step of the derivative, you're given a point, then just plug the point into that type of equation. There's really no need to solve for y prime unless the problem is just explicitly asking you for y prime. So we could have taken this equation to find the slope of the tangent at 3, 2, and we could have said, or let's just see what happens once we plug these values in. So we just took our derivative equation and plugged x, y in. Yeah, so now you just have numbers to deal with, right? We have 6 plus 3y prime plus 2 for minus 12y prime equals to 0. And so we can just collect our terms here. 6 and 2, that gives us 8. 3 and negative 12 give us negative 9y prime equals to 0. And so from here we can see that y prime is negative 8 over negative 9. I mean, the technique where we solve for y prime, you should know how to do that. It's basically just an algebraic step. But the point is if you're given this equation and it says find the slope of the tangent line at this particular point, I think it's easier just to find the derivative and then plug x, y in as opposed to solving for y prime first. Do whichever one you want to do because we see that they're the same result. I just think one's a little bit more, is a little easier. So what's the equation of the tangent line? We already have one piece of information. The slope of the tangent line is 8/9. Yeah, 8/9. We just have the fact that y minus 2 equals to 8/9 times x minus 3. We have 8/9 x. So we have 24 ninths plus 2.
6 ninths.
2. 44, 42.
It's a negative
Yeah, I think it's
24.
a negative.
Oh yeah, negative 24.
So
6
ninths.
minus 6 ninths.
Yeah.
Oops. That's the equation of the tangent line. Try that again. T.
I'm just gonna say that if I look at the equation, it's not y equals the limit of x minus 2 x.
You're good.
You got it.
And I did it all in this This one kind of just goes on its own, and that's fine.
All right, so there was the point or curve, and then the equation of the tangent line.
Nice.
You'll notice that it does cross through, right? Because this thing isn't a function. It fails the vertical line test here, maybe other spots, I don't know. No, just there. But with these in particular, if you look at if you are finding a tangent line somewhere and you graph it, you will see a lot of the times that the tangent line does actually pass through the function or the curve on another occasion, or maybe two. But the point is that we found the line that touches this point.
You see well.
Okay. Any other questions on that example?
The only other question I have is on that derivative for y cubed.
Uh-huh.
Why did you, I guess, how did you get that y prime or that derivative of y in there for the final answer of 3y squared times the derivative of y?
Okay, so again, that's because y is a function of x.
Right.
So if I said, what's the derivative of y cubed? Think about it as asking, what's the derivative of f of x cubed, right? So to take the derivative of this thing cubed, you have to use the chain rule. So we take the derivative of the outer function, where the inner function's left alone, right? And then you multiply by the derivative of the inside. So we multiply by the derivative of the inside. And symbolically, I can just write that derivative as f prime. But since f of x is y, that's y and y prime. 3 times y squared times y prime. I don't know if that's helpful. I know we just kind of went over that, but we've seen it again. Oops, I don't know.
So is the use of the power rule incorrect?
Not fully. Like if you just did the power rule, then you're not taking the derivative correctly because it's a chain rule.
So what differentiates it for you to look at that and determine that it needs the chain rule versus the power rule to be solved correctly?
The fact that I'm differentiating with respect to x. So if I take the derivative with respect to x of f of x cubed, versus the derivative. I'm not differentiating that equation with respect to y. If I differentiated that with respect to y, then that's just a power rule, because y is just y. But here, y, what we're dealing with is that y is actually a function of x. So, whatever you want to look at, that's like sine of x cubed, that's like e to the 2x cubed, the square root of x minus 1 cubed, whatever that function of x happens to be. So those are chain rules. This is just a power rule. I think it's easier to see in the context of x because we're used to working with x, right? But you just if you replace x with some generic function, then that becomes a chain rule now. It's really always a chain rule, right? If I say what's the derivative of x cubed, you say that with respect to x, you say that it's just 3x squared, right? But it's really x cubed. So you say it's 3 times the inside left alone squared times the derivative of the inside, which is just 1, right? So that's why we don't see that next to the 3x squared. So, I mean, essentially, with all of these derivatives that we've seen up to this point, all of them have been chain rules. Even the product rule and the quotient rule had a chain rule involved. But since all of those respective derivatives were just 1, you never actually saw them. I don't know if that's helpful or not, but
Yeah, I see what you're saying.
yeah. Down here. Any other questions? We can clear up. So when we also get to section 311 with related rates, how we relate two different rates together, that's all done by implicit differentiation, because maybe the x or the x variable represents something moving horizontally, the variable y represents something vertically, and we want to know like how fast are the distances changing between these two things, then we have to differentiate with respect to time. So that becomes an implicit differentiation problem for relating rates to one another as well. We see that in 311. Okay. All right, if everyone's okay with this problem, then we'll take a break.
Show me another one. Let's see how I feel.
Let's do it. Those ones like time
Usually it's
Okay, that's inappropriate. Never mind. We'll not talk about that one.
All right, let's bring it back. So the idea of what we're doing here is maybe we can solidify that by saying that you've kind of been doing that all along. So when we say that like y is equal to x squared plus 2, then we say what is the derivative of that with respect to x. I don't think anyone would hesitate at this point to say that it's 2x, right? But notice on the left-hand side, we've been doing that the whole time. The derivative of y is y prime with respect to x. The derivative of x squared is 2x. So you've been doing that all along. Maybe you're just, we're not really thinking about that when we're taking the derivative, but that is exactly what's happening. Of course, it gets a little more obscure or more abstract when we say, what's the derivative of x cubed y to the 4th? But that's the point, is that this is a little more abstract because the equations or the curves that we're dealing with are a lot more complicated than just saying y is equal to x squared or something to that effect. So we do have to have a little bit of abstraction to get by that. So I don't know if that's a helpful way to look at it, but you have been doing that all along too. Okay. So find the equation of the tangent line at 1, 1 on the following curve, given by x to the 2/3 plus y to the 2/3 equals to 2. So again, we start off by taking the derivative of both sides of our equation. What's the derivative of x to the 2/3?
2/3 x minus raised to the power of negative 1/3.
Okay, right, so the power rule there. Remember, times the derivative of x, right, which is just 1, plus the derivative of y to the 2/3. What's the derivative of y to the 2/3?
It would be 2/3 y to the negative 1/3 y prime.
Okay, 2/3 y to the negative 1/3 times y prime is equal to the derivative of 2, which is 0. So take the derivative of things normally. With the y's, you just add on a y prime, or multiply by a y prime, rather. Now, we could, of course, solve for y prime, but again, I think it's easier, since we're actually just given a point, to find the slope of the tangent line directly plugging into the equation that we have here. So if x is equal to 1 and y is equal to 1, what we have is 2/3 times 1 to the negative 1/3 plus 2/3 times 1 to the negative 1/3, and all of that right there is times y prime equals to 0. So we have then 2/3 plus 2/3 times y prime equals 0. Two-thirds y prime equals negative 2/3, which means y prime is negative 1. So that is the slope of the tangent line at 1, 1.
This may be more complicated, but could you factor out the 2/3 in both and like simplify it that way? Would that work as well?
Yeah, right. You can multiply both sides of your equation by 3/2 even to clear that out.
Yeah.
Yeah, and then you would get a negative x to the negative 1/3 over y to the negative 1/3 for y prime. Does anyone have any questions on the derivative itself, that first step? Okay, so we've got a slope of 1, then the equation of the tangent line at 1, 1. Y minus the y coordinate equals to the slope of the tangent line times x minus the x coordinate. We have y equals negative x. We have 1, 2. So the equation of the tangent line is negative x plus 2. questions on that? All right, so we can also use this method to find second, third, fourth derivatives, etc. The thing with higher order derivatives when we use implicit differentiation is typically you're going to reference the first derivative, and you could reference the original equation to simplify that. So we saw that the first derivative was negative x over y. So to take the second derivative, what do we need to do?
Implicitly differentiate the first derivative.
Yeah, take the derivative implicitly of the first derivative, and the first derivative consists of what? What rule? Quotient, yeah. So you've got to use the quotient rule to take the second derivative. So we say the second derivative is the bottom times the derivative with respect to x times the derivative of the top minus the top times the derivative of the bottom. Let me just write it out. Times the derivative of the bottom all over the bottom squared. So we have negative 1 times y, or negative y, plus x times the derivative of y. So that's plus x y prime. And then all of that's over y squared.
And there's no way to simplify that.
Yeah, so there is a way to simplify that. Well, we have a y and a y prime up top. We could write both of them over y squared and split that up, but we still have other simplification that needs to take place. So the quotient rule applied to negative x over y. Does anyone have any questions on how we got there? So y prime, we know what y prime is. So we're going to put that back into the second derivative and say that the second derivative is negative y plus x times y prime all over y squared. So like the first derivative is in terms of x and y, your second, your third, your fourth derivatives should be in terms of x and y as well. It's like saying this derivative is equal to the first derivative times some other stuff is improper in the sense of like solving for x would be improper to say that x is equal to 2x plus y, right? So higher order derivatives need to also be in terms of x and y, not lower order derivatives. So and to simplify from here, it's the same tactic you always use when you have complex fractions. You're just going to clear the complex fraction on the top. Well, rather, we're going to clear the smaller fraction by multiplying both top and bottom through by y. So from here, we're going to multiply by y. Or 1, rather, y over y. So we have y double prime. The second derivative is negative y. Let's just write it out. Multiplying by y over y. Right, yes. So we have two terms on the top. So we need to distribute that y. So you've got a negative y squared got a negative x squared all over y cubed.
Wouldn't it be negative xy squared? Or
Mm.
x squared y, I guess?
For the second term on top, no, the y divided by y cancels.
Oh.
So there we have our second derivative in terms of x and y. You could leave it like that, but we can simplify that even further by doing what? Well, we couldn't factor out y from the top. Maybe we could split that up and say it's negative y squared over y cubed minus x squared over y cubed. We can actually do better than that.
I was gonna say, can't we write it as negative y squared over y to the third minus x squared over y to the third?
Yeah, you can.
Okay.
But we can do better.
The top is a difference in squares.
Yeah, the top is a difference of squares, but also the top is what?
Oh, heck. 1.
The top is not 1. The top is negative 1, right? Because if we know x squared plus y squared is 1, then I know if I negate that equation, I have negative x squared minus y squared equals negative 1. And that's what I have in the numerator of my second derivative. Negative y squared, negative x squared. So I don't know if that's absolutely necessary, but it is certainly a whole lot simpler than negative y squared minus x squared over y cubed.
That only applies to this problem.
Yeah, to this problem. If you have another second derivative problem, you want to look at your first derivative, plug that in, and then you want to look at the original equation, or the original equation, and try to use that to simplify as well. Any other questions on that example? Okay. So I do want to mention that if you're looking at the my math lab help me solve this, they're not gonna. So just let me write something down. If you're taking the derivative of I don't know, y squared, we've been saying that this is 2y times y prime. MML is going to call y prime dy over dx. So that's just our alternative notation for derivative, dy dx, y prime, f prime, it's all the same thing. So just a word of caution. Okay, so find the derivative of sine 2y squared minus 8x equals to 5e to the y. So the first term, sine of 2y squared, what rule's involved with that? Chain rule. So we take the derivative of the outside, leave the inside alone, then do what?
Take the derivative of the inside.
Yeah.
Put the derivative of the inside.
Then we multiply that by the derivative of the inside. Yeah, does everybody agree? Okay, derivative of negative 8x. Derivative of 5e to the y. What would that be?
5e to 5ey. Wait, no.
Nope.
Would that be another chain rule? 5e to the y prime?
Yeah, it's another chain rule. Let's just write it like this. This is 5, the constant, times the derivative of e to the y. So let's take those derivatives and work those over here. The derivative with respect to x of 2y squared would give us what?
4y prime.
4y y prime? What do y'all think? 4 times y prime? Okay. What's the derivative of e to the y?
E to the y prime.
Yeah, e to the y. Remember, the derivative of e to any power is e to that power times the derivative of its power. E to the power times the derivative of its power. So e to the y prime, or y prime e to the y. I'm going to write that.
I'm a little confused at the top where it says it's 5 times derivative of e to the y. Shouldn't it, why isn't it 5 e to the y times, or why isn't it like the derivative of the outside and leave the inside alone? So why isn't it 0 times e to the y?
So that's for like a constant function times, or constant times a function of x.
Okay.
Right, so we just have a constant times a function of x, because this is just 5 times e to the f of x. Yeah. So the constant is 5, we just pulled that out. You could have kept it in there, right? We could have kept it in there and said the derivative of 5e to the y is 5e to the y prime.
Right.
If that makes more sense, then maybe do that instead. So we got to fit that stuff in here. It's cosine of 2y squared times 4y y prime minus 8 equals to 5 times y prime times e to the y. Questions on that? If this were cosine of 2x squared, you would say it's sine of 2x squared rather. The derivative is cosine of 2x squared times 2x. But again, we're taking the derivative with respect to y, so we just have that additional multiplier of y prime. Okay, we've got to solve for y prime. It really doesn't matter what side you put it on, but both of these terms, with the cosine and with the e to the y, both of those terms need to be on one side together. So we'll just put the primes on the left and move the 8 over. Then we're just, since both terms have a y prime, we just factor that out. So on the left, we just have y prime times cosine of 2y squared times 4y minus 5e to the y equals 8. And then so y prime is 8 over all of that stuff in the brackets. Anyone have any questions on that example? All right then, well, that's 3/8.
Yeah. Do you want to blank? Yeah, I saw that with that, and I looked at.
Yeah, I think, yeah.
I just want to make sure, because things for each section.
Yeah, this is just one page. So here in 3.9, we're looking at derivatives of the logarithms and exponentials. So what we're going to take these in order. First, we're going to look at how to take the derivative of the natural log of x. Then we're going to look at the derivative of an exponential, b to the x. Remember here with this one, b is larger than 0 and not equal to 1. And then finally, we'll look at the derivative of the generic logarithm, the log base b of x. So these properties of e to the x and ln, they're inverses of one another. But these properties are utilized for the derivative of all three of those. Maybe not all of those properties, but we will utilize those properties to justify the derivatives of those three functions. So the first one we're going to look at is the derivative of y equals to the natural log of x. So at this point, we don't have a shortcut to take the derivative of the natural log of x. I guess the more difficult approach would be to say, what's the limit as h approaches 0? Ln x plus h minus ln x all over h, and compute that limit. That would give us the derivative for the natural log. But we have other techniques that we can use to make this a bit easier. So, namely, if y is equal to the natural log of x, what is x? If x is 1, y would be 0. If y is the natural log of x, then x is equal to any one of those three help? Yeah, the second one, right? If y is the natural log of x, if and only if x is equal to e to the y. Remember, that's just the definition of a logarithm. Do y'all remember that? If y is the log base b of x, then that equation is, or that statement is equivalent to saying b to the y equals to x. So you roll the logarithm to convert it from a logarithmic to an exponential form. So that's just the property here. We've got y equals the log base e of x, which means that, we'll just write it here, that e to the y is equal to x. All right, that's the same statement. So instead of wondering what the derivative of y equals the natural log of x is, the same statement is y equal, or e to the y rather, is equal to x, and we'll take the derivative of that statement, because I know how to take the derivative of e to a power. But this is implicit. It's implicit what y is, if we say e to the y equals x. So we take the derivative of e to the y with respect to x. The derivative of e to the y with respect to x is what? E to the y times y prime. We just did that in that last example. So this is e to the y times y prime, and the derivative of x is 1. So then we solve for y prime and say y prime is equal to 1 over e to the y. But what's e to the y?
X.
E to the y is equal to x. So what we've shown is that the derivative of the natural log of x is 1 over x.
Can you scroll up again?
Sure, yeah, sorry.
So it basically just said y equals ln x, or natural log of x, and e to the y equals x are the same thing?
Yes,
Okay.
right, yeah, by the definition of logarithm, what a logarithm is. So that property 2 is specified at the very top. That's just the definition of a logarithm. It's how we define what a logarithm is. So it's odd to think about, like, logarithms come in to solve exponentials, but we think about logarithms in terms of an exponential. Let's write the more general statement down. This is helpful only in this sense. You've got to remember the chain rule. That's the most widely used of these. So in general, we'll look at the derivative of the natural log of any function of x. Not just x to the first power. So what would the derivative of the natural log of f of x be? 1 over f of x, right? Because here's the derivative of natural log of this argument. It says it's 1 over the argument. So this is 1 over f of x. Are we missing anything?
We need the f of x prime.
Right. So we have 1 over the argument. That's the derivative of the outside, right? So that's how to take the derivative of the function when the outer function is the natural log. It's 1 over that thing. But then the chain rule says you have to multiply by the derivative of the function on the inside.
So did you say f prime of x over f of x?
Right. So that's f prime of x over f of x. So I think this one here is a little bit more conducive to commit to memory. So that's how we take the derivative. The natural log of any function of x is 1 over the function times the derivative of the function. Or if you want to think about it, it's 1 over the argument times the derivative of the argument. Okay, so examples. What is the derivative of the natural log of x squared? So we say the derivative of natural log of that argument It's 1 over the argument times the derivative of the argument. So you have 1 over x squared times 2x. Which is just 2 over x. Any questions on that? So who remembers the properties of logarithms? Some people do for sure. What can I do to the natural log of x squared by the properties of logarithms?
Should you take the power out front?
Yeah. So the log of anything raised to a power, you can bring the power out front to multiply the logarithm. Right, so the derivative of ln x squared is the same thing. I'm going to simplify first before I take the derivative. It's the same thing as taking the derivative of 2 natural log x. Well, 2 is a constant times a function of x, so that's 2 times the derivative of the natural log of x, which we said was just 1 over x. So 2 times 1 over x, or 2 over x. Same thing we got there. You should remember, if you're not familiar with properties of logarithms, definitely look those over by next class, because we look at a process in this section called logarithmic differentiation, which pretty much heavily depend on the properties of logarithms. That's one property of logarithms. There's 2 other ones for sums and differences, or products and quotients. All right, example 2. Sorry. What's the derivative of the natural log of sine x? That's a chain rule, yeah. Does everybody see that's a chain rule? The easiest way to tell like a chain rule versus a product rule, like this is a chain rule, the natural log of x, sine x is a product rule. Just a matter of how many x's you have in there, right? So product rule on the bottom, the natural log of sine x is a chain rule. So what is the derivative of the natural log of sine of x?
Negative cosine x over x.
Careful. So it's we're taking the log of sine of x.
Oh, cosine x.
Close. Cosine x over, not just x, sine x, right? Derivative of the natural log of this function is 1 over that function. 1 over that function times the derivative of that function. So that's cosine over sine. Sorry, cotangent, right. I heard tangent. I wrote a T. So, you know, whatever. Whatever you like here. Questions on that example? So if you've got the log of something, the derivative is just 1 over that thing times the derivative of that thing. Example 3. What's the derivative of the natural log of e to the 2x? Yeah, 1 over e to the 2x times the derivative of e to the 2x. So what's the derivative of e to the 2x? Yeah.
2
Yeah.
to the 2x.
2 times e to the 2x over
E to the 2x.
e to the 2x. Remember, the derivative of e to any power is e to that power times the derivative of its power.
Those cancel out.
Yeah, those cancel out, and we're left with 2.
You can skip that whole process though, because
Yeah.
the natural log of e to the 2x is just 2x.
Right,
So the derivative of 2x is 2, so theoretically, and you don't have to do anything.
right. So the properties of natural logs in e to the power of x, they're inverses. The natural log of e to any power is just the power itself. That's like taking the square root of x squared, or the cube root of x to the third. They're inverses. So, you know, honestly, we could have just saved a lot of time and said that this function on the inside is equal to just 2x. And the derivative of 2x is 2. What about the derivative of the natural log of the natural log? No, 1. Not quite. So is this what kind of rule are we using here?
Would it be a chain rule?
It's a chain rule. Yeah, there's only one x present. It's not the ln x times ln x. It's the log of x. So here's your argument. The outer function is the natural log. So this is just, look at this as the natural log of f of x, right? So 1 over the argument times the derivative of the argument. So you've got 1 over ln x times 1 over x. You're right. So that's 1 over x ln x. Don't say that's 1 over x, or sorry, 1 over natural log x squared. You can't combine those two. It's 1 over x ln x.
So would it be incorrect to write 1 over ln xx?
No, I mean, I think when people, when people write 1 over x, or sorry, 1 over ln x times x like that,
Yeah.
you know, it's, if you have to do more with that problem, you might just say, oh, that's the natural log of x times x.
It looks like the natural log of x squared almost.
Yeah, so I mean, is this?
No.
Depends, right? Depends on what you're doing. If I say I'm taking the natural log of that, right? Typically the textbook or the homework doesn't put parentheses around the logarithm. You're taking the logarithm of whatever. It's super clear when you have the parentheses, but for whatever reason, that's not like a common practice. So it's whatever follows the logarithm is what you're taking the logarithm of. So usually other stuff is put in front of the logarithm to distinguish between one or the other. But yeah, if you write 1 over ln x times x, as long as you know what that means and what you're doing with that, that's fine. But I would, to avoid confusion, I would just put the x out front like that. All right, questions on any of those? The derivative of 4 or natural log? Here's the next one on. So we'll look at the derivative of exponential functions. So with this rule, it's super crucial that you realize when you're applying a power rule versus when you're applying the exponential rule. And it's if your variable is in the exponent, it's always an exponential. If the variable is in the bottom raised to a number, then that's just your power rule. So you got to keep those straight. Yeah, I mean, b is a real number that's larger than 0, not 1. So we could, again, apply the definition of the derivative, or we could just try to rewrite this algebraically. To maybe look at something that we already know the derivative of. So for b to the x, which one of these properties helps us here? Yeah, property number 3. It says for real numbers x and b larger than 0, b to the x is the same thing as e to the ln of b to the x, right? So again, just utilizing properties of inverses, e to the ln of anything is just that thing, because they're inverses of each other. So that's the property we're going to use. We're going to rewrite b to the x as e to the natural log of b to the x. And then the power itself, ln of b to the x, we use the property of logarithms, because that's the log of something to a power. So the power comes out front to multiply the logarithm. So not writing it as e to the x ln b doesn't really do you any favors, because if you say, well, I've got to take the derivative of e to the ln of bx, b to the x rather, you're still stuck with the same problem of what is the derivative of b to the x. So if we can write it like this, the property of logarithms allows us to look at it indirectly. Instead of taking the derivative of b to the x, we'll take the derivative of e to the x ln of b. So what is the derivative of e to the x ln b? So that's just the derivative of e to a power. So the derivative of e to that power is e to that power times the derivative of the power. So it's the derivative of x times ln b.
X over b.
So careful, what is b though?
Oh, wait.
B is a constant. So the ln of b is also a constant. Right? B is just some number bigger than 0, not 1. So if b is a number, the ln of that number is yet another number, right? So what's the derivative of this number times x? Just that number, right? What's the derivative of 2 times x? It's 2. What's the derivative of negative 27 times x? Negative 27. What's the derivative of x times this number, it's just that number. So you have e to the x ln b times ln b. But what is e to the x ln b? What is that? It's y, and y is b to the x, right? So this is b to the x. That's the derivative of b to the x. It's b to the x ln b. So we'll look at the chain rule here in a second, but does this make sense if y is equal to e to the x? Well, if y is e to the x, then our b is simply equal to the number e, right? So we know that, let's apply this rule. It says to take the derivative of any exponential, we take the exponential as it is, and then multiply that by the natural log of its base. What's the natural log of e? 1. It's 1. So that's...
How did you go from e to the x, to the x?
So that's this, which was that,
Okay.
which was that, which was that. So that's really all we need to take away, just the derivative formula. I won't ask you to derive these on the exam. Just I feel like the ones that we can show where they come from, we should, because otherwise it's kind of like, okay, well, we'll just accept that as truth. If we can show why that's true, then I think we should. So in general, the derivative of b to some power f of x, again, this is just the chain rule. Here in blue, we've got the derivative of the outer function when it's exponential. So the derivative of b to the f of x is b to the f of x times ln b. And then that's the derivative of the outer with the inner function left alone. And then the chain rule says multiply that by the derivative of the inner. Any questions at this point? We'll look at examples on Tuesday. So look over properties of logarithms and try to catch up on the homework. See ya.